For the first series of questions, you're asked to evaluate each statement and determine whether it's true or false. Alkanes contain only carbon and hydrogen. Remember that alkanes are basically molecules that have nothing but carbon-hydrogen single bonds, so that statement is true. Alkanes are soluble in water. Alkanes, being molecules that only contain carbon and hydrogen, are basically nonpolar, and so therefore they are not soluble in water. So that statement is false. Alkanes contain sp3 hybridized carbons only. That is true because they only contain carbon-carbon single bonds. If they had double or triple bonds, that would be sp2 and sp. Straight-chained alkanes have higher boiling points than branch-chained alkanes. If you go back very early in the semester in Chemistry 221, what you will find is that when we talked about straight-chained alkanes, they have the ability to pack very closely together, and so therefore they have their intermolecular, the strongest intermolecular force is dispersion, and so therefore dispersion, the strength of dispersion forces is based on the surface area contact, and so straight-chained alkanes are able to compact together fairly well, and they're able to share a lot of surface area. If you have a branch-chained alkane, they are much more spherical in shape, and so they would only have smaller contact, and so therefore they will have less of an intermolecular force. So because the straight-chained alkanes share a lot of surface area, they have stronger intermolecular forces, and so therefore they will have higher boiling points. So that statement is true. A cyclohexane ring flip results in all the equatorial hydrogens to become axial and vice versa. Remember what a cyclohexane ring flip is. In a cyclohexane ring flip, I'm going to bring this carbon up, which will form a boat, and then I'm going to bring this carbon down to form the ring flip. So the ring flip is going from here to there. In that process, hydrogens that are axial in this case become equatorial and vice versa. So that statement is actually true. It says a cyclohexane ring flip occurs through the boat conformation. That is also a true statement. Why? Because as we bring this carbon up, we end up in the boat, and then we bring the other carbon down. This is a ring flip. Cyclohexane ring flips occur when ring is rotated 180 degrees. That is false, because the ring flip was, as I just showed you, the idea that the ring stays stationary. We just move one carbon up and the other carbon down. We don't actually rotate the ring, so that's false. When a reaction becomes more endothermic, it'll occur faster. Well, let's draw a reaction coordinate diagram. So let's draw two reactions that are endothermic. And let's draw another one that is more endothermic. So remember that, and the idea of making it more endothermic is to basically, in this case, increase the energy of the products. So looking at these two diagrams, will it occur faster? Well, which one of these two reactions has the smaller activation energy? The one with the less endothermic. So when a reaction becomes more endothermic, it has a higher activation energy. It will occur slower, so that's false. When a reaction goes through a more stable intermediate, it will go faster. Well, again, I can draw a reaction coordinate diagram going from reactant to intermediate. So here is my intermediate. If I make the intermediate more stable by having a lower energy, what happens to the activation energy? It gets smaller, and therefore the reaction goes faster. So that is actually a true statement. Let me just go back and review here for a minute. Remember that according to the Arrhenius equation, rate is equal to A e to the minus RT EA over RT. So, therefore, the larger the activation energy, the slower the rate, because it's e to the minus EA over RT. The higher the temperature, the faster the reaction goes. Hammond's postulate states that in an endothermic reaction, the transition state resembles the reactants more closely. Alright, let's draw the reaction coordinate diagram for an endothermic reaction, which we've already done, but it looks like that. Where is the transition state? In this case, the transition state is here. What does that look like? Well, that more closely resembles the products than the reactants. So in an endothermic reaction, the transition state resembles the products more closely. So therefore that statement is false. The transition state in an exothermic reaction will have a higher activation energy when the reaction becomes more exothermic. All right, so now we've got to again draw a reaction coordinate diagram. Here's my exothermic reaction. The transition state will have a higher activation energy when it becomes more exothermic. If I write the reaction being more exothermic by writing a lower product energy, what happens to that? The transition state energy actually, it has a lower activation energy. So that should be lower. So that statement is also false. The reaction rates will decrease when the temperature of a reaction increases. Again, looking at the Arrhenius equation here, when you increase the temperature of a reaction, the reaction rate increases. So again, that statement is false. And a tertiary carbocation is formed slower than a secondary carbocation. If I drew a reaction coordinate diagram, I would have a tertiary carbocation there. Where would the secondary carbocation go? The secondary carbocation would go there. Which one has the lower energy? The tertiary carbocation, which is more stable. Therefore, it has the lower activation energy to form. Therefore, it is formed faster. And so that statement is false. All right, for each of the structures below, indicate whether it's an intermediate, so unstable that it won't form, an intermediate that is very unstable, and that would include transition states, but it will form. C, a moderately stable intermediate, a very unstable intermediate. D, or its incorrectly drawn structure. Let's start with a primary carbocation. Do primary carbocations form? The answer is no, they do not, so therefore that falls into category A. A primary radical. Well, primary radicals do form, they're not very stable, and so I would place that into category B. It's not very stable, but it does indeed form. This is a secondary carbocation. Secondary carbocations are stable. They're not very stable, so I would place that into category C that it's moderately stable. Well, let's see. We'll do question 22 here. This structure looks like a transition state because I have a partial bond. This transition state would be the one that is formed when this alcohol reacts with H+. So this hydrogen is missing a delta plus charge. So therefore, this structure is drawn incorrectly. Looking at this one, it's the same transition state, or supposed to be the same transition state, but as this alcohol gets protonated, the oxygen goes from 0 to +1. That should not be delta minus, it should be delta plus, and so therefore that structure is drawn incorrectly. So both of these are incorrectly drawn structures for this transition state structures for that reaction. And I'm giving them to you because I saw a lot of those last semester, so you want to make sure that you draw that transition state correctly. Well, let's go back to 17. Methyl carbocation, extremely unstable, doesn't form, therefore we'll put it in category A. Methyl radical, unstable, does form, so we put it in category B. Number 19, it looks to me like that is the transition state for taking a carbocation and adding H2O to it, like so. Is that the correct transition state? No, because the correct transition state, or the final product would be this oxonium ion. The oxygen is going from 0 to +1. That oxygen is not delta minus, it should be delta plus, and so therefore that structure is drawn incorrectly. Number 20, 5 bonds to carbon, drawn incorrectly. 421, we have a transition state for an E2 reaction. What transition state does an E2 reaction undergo? Are anti-periplanar transition state. Is this anti-periplanar? No, this is actually periplanar. So this is incorrectly drawn. What should it look like if it was to be correct? The NH2 would be partially bonded to the hydrogen, which would be partially bonded to the carbon with another partial double bond, and then the chlorine would be down there. And so this would be delta minus, the chlorine would be delta minus. Over here we would have the H, we would have the methyl group, and then I'd have to rotate this bond 180 degrees, so that would put, let's see, the way I would do that, that would put the ethyl group forward and the methyl group back. So this would be the correct E2 transition state for that reaction. So anyway, 21 is incorrectly drawn. 24 looks like a transition state of an SN2 reaction where I'm taking Br minus and adding it to this oxonium ion where the water molecule is leaving. So this looks like the transition state of that reaction. The final product then would be that. So looking at the transition state, is it correct? Well, yes, Br would be delta minus. This is trigonal bipyramidal, that's good. However, that oxygen is going from +1 to 0, therefore it should be delta plus, so that is an incorrectly drawn transition state for SN2. For 25, we have an E2 reaction. Our tertiary butoxide is coming in to deprotonate this hydrogen. Everything in this transition state looks good, except remember that the hydrogen needs to be trans to the chlorine, and in this case that hydrogen is not trans to the chlorine, the one that's being deprotonated. So this is incorrectly drawn. If I wanted to draw it correctly, I would not draw the tertiary butoxide deprotonating that way. I would draw the tertiary butoxide deprotonating the hydrogen that is trans to the leaving group. Okay. (26) This looks like a transition state of the following step in free radical halogenation. What's missing? That should be a partial bond. That would have been correctly drawn. Here's the transition state for the following. Transitions or following step in free radical halogenation. The one where the chlorine is dissociated with the alkyl radical. What's missing here? Nothing. It's actually correct. It's the only one that's correct. And so that would put us at group B, which means that this is the correct transition state. Alright, pairs of reactions, which one occurs faster? So we went over this in class on Friday a little bit. Let's just go through the steps really quickly. The first thing that I need to know for each one of these reactions is it SN1 or is it SN2? And then I would need to know what's different about the two reactions. And then does that difference matter? And if so, which reaction goes faster? So we take this reaction. This is a primary halide plus a nucleophile. In this case, it's actually fairly straightforward. We've got the top reaction would be go by an SN2 mechanism. The bottom reaction would actually be no reaction, because primary plus neutral nucleophile is a no reaction. Therefore, A goes faster. These two mechanisms are SN1. Why? Tertiary halide plus nucleophile, strong or weak. Tertiary plus a strong or weak nucleophile always gives an SN1 mechanism. What's different? What's different about the reaction is the nucleophile strength. Does nucleophile strength matter for an SN1 reaction? Remember, for an SN1 reaction, the rate determining step is to take the alkyl halide and break it apart to form the carbocation and the halide ion. That's the rate determining step. Anything that shows up in the rate determining step will affect the reaction. In this case, the rate determining step does not. This does not include the nucleophile, and therefore, in this case, the nucleophile strength doesn't matter. And so this would be C. This reaction would occur at the same rate. Now for 30, we've got primary halide, strong nucleophile. That mechanism is SN2. Now, what's different? The solvents. For an SN2 reaction, I have my nucleophile coming in, attacking the carbon, kicking off the leaving group. And when we talk about solvents, hydroxylic solvents will solvate the nucleophile better. Well, what does that do? That ends up slowing the reaction. And so therefore an SN2 reaction goes faster in a non-hydroxylic solvent, because the non-hydroxylic solvent doesn't solvate the nucleophile as much. When the nucleophile is really solvated, it's got to lose all of its solvent to form or to react with the halide. Now for an SN1 reaction, if we can actually take these and if we solvate those better, we make the products more stable. And when the products become more stable, the reaction goes faster. So SN1 reaction, their rate increases with the hydroxylic solvent. So coming down here then, we've got an SN2 reaction. Which solvent is going to cause the reaction to go faster? Water will actually slow it down. So the faster reaction is A, because it has the non-hydroxylic solvent. If we now go to the other side and we go to question 31 here, we now have a tertiary halide and weak nucleophile. So this is now an SN1 mechanism. Which reaction goes faster? Well, the difference is solvent. In this case, this one would be sped up by the hydroxylic solvent. That increases the rate, and so therefore B would be faster. For C, or for 32 here, I've got a tertiary halide, a weak nucleophile. The mechanism is SN1. Now, in this case, what's different? What's different is the leaving group. Does the leaving group play a role in the reaction rate? Yes, if it shows up in the rate determining step. So let's go back again to the rate determining step of an SN1. Alkyl halide breaks apart to form carbocation and X minus. Is the leaving group in there? Yes. So therefore, the better the leaving group, the faster the reaction. Now our only question is, what's the better leaving group, chloride or iodide? Well, remember that leaving group ability is based upon one thing and one thing only, and that is basicity. And it is inversely related to basicity. So now coming back here, will this play a role? Yes. Which leaving group is better? The better one is going to be the weaker base. Which one is the weaker base? Iodide or chloride? I minus is the weaker base, and therefore I minus is the better leaving group. And so B will go faster. Okay, question 33. Stereochemical relationship between 2R3S and 2S3R. Now, under most circumstances, what we could probably do is quickly look at this and say one chiral center is opposite, the other chiral center has opposite configuration. When two molecules have opposite configurations for each and every chiral center, they are normally enantiomers. However, I have a sneaking suspicion that we need to check this molecule to see whether or not it is meso. So, Let me draw out my butane. I'm going to have a chlorine here and a chlorine here. So there's 2,3-dichlorobutane. I'm going to take my Fisher projection. I'm going to write my hydrogen there and there because I want the hydrogens to be on the positions away from me so I can determine R and S. How about this is carbon 2, this is carbon 3. Let me put a chlorine here. If I put the chlorine in here, then chlorine would be number 1 group. This group down here would be number 2, and the methyl group would be 3. So if I put the chlorine in this position, what's the configuration? The configuration is going in this direction. So actually, I should put my methyl group there and put my chlorine here. Now chlorine's number 1, this group is number 2, the methyl group is number 3, hydrogen is 4 away from me. That means that I'm going counterclockwise. So now I have the 2R. So this is the 2R configuration. Coming down to the bottom carbon, where am I going to put my chlorine to make the S configuration? If I look at that, I want to put the chlorine here so that the chlorine would go, so that going group 1 to group 2 to group 3 on this side would now go, it's going clockwise. So that would be R, so I messed that up, so I need to put the CH3 there, and I need to put my chlorine here. Now if I put my chlorine here, I'm going group 1, group 2, group 3. That means from 1 to 2 to 3 is counterclockwise. Now I have the S. So here is the 2R 3S configuration, and guess what it is? It's meso. So if I now write the 2S3R, what's it going to look like? Well, it's going to be the mirror image, right? So here are the mirror images. This one is 2R 3S, and this one is now 2S 3R. But guess what? They are the same meso compound, so they're not enantiomers. They are the same meso compound A. Trick question, I guess, if that's what you want to call it. But we always have to check for meso. Right, so now using the same choices, what would happen if I had 2R 3R? Well, let's just write the structure of 2R 3R using the configurations from above. So that means methyl group here, hydrogen there, chlorine there, and now the R from below had the chlorine here, the methyl group here, and the hydrogen there. Is that meso? Nope. It's not meso, which means now if I write 2R, 3R, and the 2S, 3S, the mirror image of that is going to look like this. What are they? They are enantiomers. So you always have to check. That was a tough question from last semester. Okay, using the reaction below. First of all, what's the mechanism of this reaction? This is a secondary halide plus a strong nucleophile. Mechanism SN2. Alright, so SN2 means what? That means this is going to attack from behind, Bromine's going to get kicked off. The final product is going to look like this. Alright, so I'm going to have my inverted. So I'm going to have inversion of configuration. Alright, so let's take these questions one at a time then. Alright, inversion of configuration. The product of the reaction would be S. I don't know. Let's determine what the configuration of the reaction is. So if I look at this, this is group number 4, this is group number 1, this is group number 2, this is group number 3. Is 4 pointing away from me? No, so I'm going to switch 4 and 2, and 1 and 3. So what is the configuration of the original molecule? Well, going from 1 to 2 to 3 is clockwise, so that makes that molecule, that makes that R. If we undergo inversion of configuration, the product is indeed S, so that is true. The specific rotation of the product would be 0 degrees. False, because this is SN2. I am making an optically active product. I am not making a racemic mixture. That'll be in the next set. The product of the reaction would be D. I don't know in this case. Is the R configuration D or L? We don't know, because there is no direct relationship between R and S and D and L. Therefore, is the product D? I don't know. And if I don't know, that statement is false. But I do know that the configuration of the product is S. That I do know. Same thing for this reaction. What's different about the two of them? Well, this is a tertiary halide plus a strong nucleus or nucleophile. What mechanism is that going to be? SN1. What does that mean? Well, that means that the specific of the product's going to be a racemic mixture. So is it going to be 0? Absolutely. The product of the reaction would be S and R, 50-50. So that statement is false. The product would be D. Yeah, it's going to be D and L, 50-50. So that statement is also false. So we do end up with a racemic mixture and a 0 degree specific rotation. Alright, regio-stereoselective, both or neither. Well, it'd be helpful if we kind of took a look at these reactions. Maybe we want to write the products of them, or maybe we just want to follow some of the rules that we learned last semester. HBrH2O2 adds an H and a Br. Anti-Markovnikov, and it adds at 50%, 50-50 cis and trans. Stereoselectivity? No. So is this reaction stereoselective? Absolutely not. Is it regioselective? Yes. Because in this case, I'm going to add the A. This is anti-Markovnikov, so the H is going to go there, and the Br is going to go there. That's the major product, and the minor product would be that one. Since I am making two different products, the major product of the reaction is a structural isomer, and so therefore this reaction is a regioselective. 42. Product of that, the major product of that reaction would be adding the H to the end carbon, the Cl there. That is the major carbon. That is the major product. The minor product would be adding the H there and the Cl. Did I make two different products? Yes. Did I select one over the other? Yes. Is this reaction regioselective? Yes. Is the reaction stereoselective? No. The major product doesn't have any chiral centers. Plus, this reaction goes through a carbocation intermediate, and anytime you go through a carbocation intermediate, you can't be stereoselective. So therefore, this one is regio only. A. 43. Is the reaction regioselective? Well, I have bromine, which adds two bromines, two Br atoms. If I have a symmetrical reagent, it is not regioselective automatically. Is it stereoselective? Sure. Because remember, bromine gets added trans. So I am forming two possible products. One where the bromine would add cis and trans. The trans would be the major product. The minor product is not formed, but it's still possible. What am I doing? I'm making two products that are stereoisomers. I am favoring one. Therefore, this reaction is stereoselective only, which is B. 44. I didn't give you any reagents. I guess everybody gets that one right. (45) This is mercuration demercuration, which adds an H, OH, 100% trans, and Markovnikov. Looking at this product, this is symmetrical. Therefore, the reaction being regioselective, it can't be regioselective because it's a symmetrical alkene. However, if I add the H and the OH, trans, 100% trans, I do make a product with two chiral centers. I am selecting trans over cis. Therefore, this reaction is indeed stereoselective only, which is, I believe, B. Symmetrical reagents, not regioselective. The major product of this reaction, though, adding both hydrogens, so this adds H and H, 100% cis. In this case, I am making a product with two chiral centers. I selected cis over trans. This one is indeed stereoselective only. Adding the Br again, symmetrical reagents. These both are not regioselective. On the other hand, this one, if I add the Brs, 100% trans. I did make 2 chiral centers. I selected trans over cis. This one is stereo selective. Adding HBr to this double bond. We know it's not regioselective. This goes through a carbocation intermediate, and so therefore this one is not going to be, in this case, because it goes through a carbocation intermediate, it's not going to be stereoselective. So that one's neither. This one was stereo only. Alright, use the products below in the 2-step reaction. I'm going to do free radical chlorination on this molecule. I've got 2 possible products when I look through this. In terms of my selectivities, in looking at this, selectivity of chlorination at room temperature is 5 to 3.4 to 1. That's chlorination at room temperature. So I've got, for A, I've got 6 hydrogens, and since those are primary, times with a 1 selectivity. For B, I've got 2 hydrogens times a 5. Sorry, this one is, there are 12 A hydrogens times 1. So there are 4 CH3 groups times the selectivity of 1. There are 2 B hydrogens, selectivity of 5. That makes 12 to 10, which means that the major product here is going to be adding the chlorine to carbon A, which is product D. Taking that major product and now adding NH2 minus to it, there is only 1 beta hydrogen for the NH2 minus to come in and grab, and so then that will leave that A as the final product there. So it wouldn't have mattered whether I used NH2 minus or tertiary butoxide, it still would have got the same major product for 50. What is the IUPAC name of the molecule below? Okay. So we've got a couple of ways to do this. We could convert this to a Fisher projection. I could take the molecule and put it in a seesaw. Let me do it that way. So let me say I'm over here looking at the molecule this way, and so the molecule is going to look like this, with the ethyl group in the up position and the other ethyl group pointing down in the plane. So this is the plane of the molecule. Then towards me is a hydrogen on that carbon, and away from me is a hydrogen there. The methyl group is pointing towards me on the front left carbon, and on the back right, the one that's pointed away is a bromine. So looking at this one, looking at the left carbon, which is, again, this is front, this is back. We should probably figure out what the name of this is. Well, that's easy enough. 1, 2, 3, 4, 5, 6. So the carbon 3 is the one with the bromine. which actually we know from the name. So the question is, which carbon is which? So looking at carbon 4 here, I've got group So looking at the groups, I've got the hydrogen is group 4, is number 4. This whole group is number 1. Methyl versus ethyl. Methyl's 2, and ethyl's 2, methyl's 3. So for carbon 4, this is the way my numbers match up. 4 is pointing away from me, so that means this is now counterclockwise, or S, which then means that that was carbon 4, so 4 is S, which eliminates then A and C. Easy enough. So now you can guess, or you can determine the chirality of the carbon on the right. Right, the one on the right, if I draw it out, it looks like that. The bromine's number 1, carbon's number 4. This whole group here is number 2, and the ethyl group is 3. Switch 1 and 4, 2 and 3. Going from 1 to 2 to 3 is now clockwise. So that means that carbon 3 is R. So I've got 3R4S, which is B. Okay, and you could have converted this Newman projection to a Fisher projection as well. That would have also been possible. All right, what's the relationship between these two molecules? These are tautomers. What are tautomers? Tautomers are molecules where they result from the simultaneous movement of a proton and electron pairs. How do you get that from here? How do you convert one into the other? Let's say we move this pair of electrons there, and then, don't do the answer keys all in one sitting. Let's move this pair of electrons there, and then that pair of electrons there to bond the hydrogen. So if I wanted to over here, I could do it this way. I could say move this pair of electrons there, move that pair of electrons there. Where did tautomers come into play? Tautomers come into play when you take a triple bond. You added H plus H2O to it to add the H and the OH to the double bond. You made an enol, and then the enol tautomerized to form the ketone. That's where that was set. That was where that showed up last semester. True-false statements about SN2 reactions. SN2s, do they occur with backside attack of the nucleophile? Yes. Primary halides react fastest? Yes. Why? Steric hindrance, less steric hindrance. When the concentration of the nucleophile is doubled, the rate doubles. That's also true because the rate equation for an SN2 reaction is rate times K times concentration of nucleophile times concentration of alkyl halide, each of those to the first power. Double the concentration of the nucleophile, double the rate. They occur fastest in non-hydroxylic solvents. That is true because, remember, as we said in one of the earlier problems, that as your nucleophile comes in to react with the carbon and kick off the leaving group, you want this nucleophile not to be solvated very well, because if it's solvated very well, it's got to lose all of its solvent before it can attack the alkyl halide. So we want solvation, but weak solvation, which are the aprotic solvents. If you use a stronger nucleophile, does the kinetic rate increase? Yes. Why? Because it's a one-step reaction and the nucleophile is in the rate determining step. Optically active products are formed if optically active reactants are true. That's true, and remember that goes by inversion of configuration. What about SN1? The kinetic rates increase if a stronger nucleophile is used? No, because the rate determining step is breaking the carbon halogen bond to form the two carbocation, the carbocation and the anion. Nucleophile is not in the rate determining step. They're usually accompanied by E1. True. Tertiary halides react the fastest. True. Why? Because tertiary carbocations are formed the fastest. Optically active products produce optically active reactants, produce optically active products. No, instead what you form is a racemic mixture. Reaction coordinate diagrams. So for each one of these reactions, we have to think about how many steps there are in the mechanism. This one is one step. This one would be 2 steps. This one would be 3 steps. Remember, these are transition states. Valleys are intermediates. So B would be 1 intermediate, C would be 2 intermediates, and A would be 0 intermediates. So primary halide with a strong nucleophile, SN1 mechanism. How many steps? 1 step, A. Secondary halide plus a strong nucleophile, sorry, that was SN2. SN2 mechanism. SN2 mechanism, how many steps? 1 step, A. Tertiary halide with a CN minus. Now all of a sudden that's an SN1 reaction. In this case I'm going to lose the halogen to form the carbocation, and the CN minus is going to react directly with that's going to be a 2-step with the carbocation. It's going to be a 2-step reaction. That's going to be B. The next set with weak nucleophiles. Primary alkyl halide with H2O. Technically that's a no reaction, so that's D. Secondary alkyl halide, that's going to be a SN1. What's going to happen? I'm going to lose my halogen to form my carbocation. My water's going to come in to form then the oxonium ion, and then alcohol. So I have 2 intermediates, 3 steps, and so that makes this one number C, because I've got 2 intermediates and 3 steps. Tertiary alkyl halide and water, again that's an SN1 reaction. That's the same thing as the above reaction. I'm going to form carbocation. Water's going to add to the carbocation to form oxonium ion. 2 intermediates, 3-step reaction for that one. Alcohol plus HCl. First step in the mechanism is going to be protonate the alcohol in each one of these to form the oxonium ion. So this one is going to be, with a primary halide, it's going to be an SN2 reaction, but I have 1 intermediate, so therefore that's going to follow the reaction coordinate diagram be? With this intermediate, with the first step being the formation of the oxonium ion, the second being the SN2 step. Secondary halide, or secondary alcohol, is first going to be protonated to form the oxonium ion, then the carbon-oxygen bond is going to break, so I'm going to form my carbocation, then my Cl- is going to add. So the important part about this reaction right here is that is going to have two intermediates, and so that's going to be then a three-step reaction, and the same thing is going to be true for 71. For each one of those, we form the oxonium ion, we lose the water to form the carbocation, and then the chlorine attacks, so that's a two intermediate. Each one of those is two intermediates with three steps, and that's C for each one of those. All right. Match the Vesper geometry to the central atom. All right, hopefully this is fairly straightforward. CH4, tetrahedral. CH4 is going to look like that. That's tetrahedral. C. CH3 plus. Oh, interesting. So a CH3 plus looks like this with an empty p orbital. What geometry is that? Trigonal planar. BH3. BH3 is also trigonal planar. Right? There's no lone pairs on the boron. But BH4 minus is tetrahedral. And H3 has a lone pair on it. And so therefore, if I'm using electron pair geometries, it is tetrahedral. NH4 plus is going to just have 4 hydrogens around it. It's tetrahedral as well. Water, using electron pair geometries, water is going to be tetrahedral. H3O plus, tetrahedral. So most of these were tetrahedral. Match a theory to a statement. Major product of a free radical reaction is the one resulting from the most stable radical. And there are no none of those match up with that, so that is E. The major product of an elimination reaction of an alcohol is the most stable alkene. That is Zaitsev's rule. So Zaitsev said when you did elimination by E1, you got the most stable product, or the most substituted product, and that is what Zaitsev's rule was. The major product of HX addition to an alkene is the one where the hydrogen adds to the carbon that has the most hydrogens. That is Markovnikov's rule. So up here, remember the Arrhenius equation I've written earlier. Rate equals A to the minus EA over RT. That's the Arrhenius equation. That gives us the relationship between rate, activation energy, and temperature. Hammond's postulate talks about the position of the transition state relative to reactants and products if a reaction is endo or exothermic. And there is, again, no statement that relates with the free radical halogenation. Rank the following bases. So I'm going to need my periodic table of CnOF, Cl, Br, I. Basicity increases from right to left. Basicity decreases as we go down the periodic table. And any of those more basic than any halide. Strongest base on the list, CH3 minus. Next, N minus. Next, O minus. So CH3 minus, N minus, O minus. 86. Now I'm down to halogens. Which one is more basic? The weakest base is chloride, which is E, and fluoride, which is C. So these three are stronger bases than the halides. As far as the halogens go, fluoride is more basic than chloride. Okay, next set of statements. Which will have a zero or non-zero specific rotation? Alright, a non-zero specific rotation means what? The molecule's chiral. A 0 degree specific rotation means that it is not chiral. Or it is a racemic mixture. Alright, molecule with an internal mirror plane of symmetry, not chiral. Single diastereomer of a compound. Good question. So diastereomers have at least 2 chiral centers. If it's a single diastereomer, it will have 2 chiral centers. If it is not a racemic mixture, it will be chiral. Meso compounds are not chiral. Racemic mixtures are not chiral. Single enantiomers are chiral. Product of an SN1 reaction and a chiral, remember that forms a racemic mixture, and so therefore that is not chiral. But the product of an SN2 reaction goes by inversion of configuration. That product is chiral. Alright, ranking the following reactions according to their SN1 and SN2 reactivities. Great. Alright, so as far as SN1 reactions go, tertiaries react faster than secondaries than primaries. As far as SN2 goes, primaries react faster than secondaries, react faster than tertiaries. In both these cases, primaries don't undergo SN1, tertiaries don't undergo SN2. Notice that I have different leaving groups in each one of these cases. Chlorine versus bromine. Does the leaving group play a role in the rate of reaction? Yes, for both SN1 and SN2. Br is a better leaving group than Cl. Why? Because Br is a weaker base than Cl minus. and leaving group ability is indirectly related to basicity. All right, let's fill this out then. SN1, what's going to be the fastest? E or F? Tertiary, right? Which one's a better leaving group? Bromine, then chlorine. So, these are both tertiaries. What's next? Secondary. Secondary bromine, faster than secondary with the chlorine as the leaving group. So there's the secondary group. Primaries. The primaries aren't going to react, so this is either A or B in both of those cases. SN2. Fastest is going to be primaries. Which one has the better leaving group? Bromine, then chlorine. Then the secondaries. Which one's faster? Bromine, then chlorine. For these two tertiaries don't react, so whether you have E or F. Basically, here you have, those are going to be no reaction. And here you're going to have no reaction. Alright, final page. Use the structures below to complete the synthetic scheme. Right. Peroxy acid. What does it do? It forms epoxides. So, I'm going to form an epoxide. So that's number 107. What happens when the epoxide reacts with H2 and palladium? I said, that one's wrong. It should be this. And what happens when H2 and palladium react with the double bond? They form that, which is E. We haven't talked about what happens when you add, if you were to add H2 in the peroxide, so I guess everybody gets credit there too. Now, these two reactions right here, if I take an epoxide, if I treat an epoxide with H plus H2O, the H plus protonates the epoxide. The water then adds to one of the two carbons so that I end up basically opening up the epoxide with two OHs. So 109 is A. And these two OHs are automatically trans because the epoxide is a triangular intermediate. If I open this up with an alcohol, I'm going to protonate the epoxide to make the oxonium ion. The alcohol is going to end up adding to the more substituted carbon in the epoxide. So that means that of the products that are there, it's going to be product C because it's going to add to the more substituted product. So then I'm going to have a trans relationship between the OR and the OH group with the OR group adding to the more substituted, so that will end up being C. Okay, so